Welcome back. In this lecture, we will discuss this particular uh, manuscript. It's a brief 3-page manuscript. It has an interesting title, Where Do Batteries End and Supercapacitors Begin, suggesting that in some ways, both batteries and supercapacitors are similar. In some ways, they differ. And the central idea behind this manuscript has become quite important in the last 10-15 years. It's more like a perspective article addressing an important feature that is critical for accurate description, especially of certain kind of supercapacitors. We'll move on. So what are the similarities between batteries and supercapacitors? Both are energy storage devices. Both batteries and supercapacitor. By supercapacitor, we are referring to electrochemical double layer capacitors. Both rely on certain electrochemical mechanisms, but the mechanisms are quite different. For battery, the mechanisms involve Faradaic reaction. There is electron transfer electrochemical reaction. However, for a supercapacitor, we are typically relying on non-Faradaic mechanism. For a capacitor, the energy storage mechanism in the most rudimentary electrochemical double layer capacitor is just the charging and discharging of a double layer. So in any case, we are dominantly dependent upon non-Faradaic mechanism. There is not significant amount of electrochemical reactions that are taking place in a supercapacitor. So the main difference is the mechanism of implication to the main difference is two. Batteries have relatively high energy density, but low power densities. That is, even though they may be good at storing significant amount of energy per unit mass, they cannot rapidly discharge or charge. That is, this is the advantage of a battery, this disadvantage of a battery. As opposed to that, so supercapacitors have the disadvantage of low energy density, but they have very high power densities. That is, they can charge and discharge quite rapidly. So these two characteristic features of batteries and supercapacitor are because of the underlying mechanism. As I mentioned in the earlier slide, so batteries rely predominantly on Faradaic reactions for obtaining high energy density. Consequently, they have low power densities because Faradaic reactions often involve activation barriers, multiple electron transfers, so their typically rates are low. Whereas supercapacitors often rely on either charging, discharging, because of at the double layer, or even if there's Faradaic reaction, it's only on the surface. So we will move on. We have addressed some of these issues in earlier lectures too. Please refer to them. So the central figure in this manuscript is this figure. It has a lot of information. We will dissect the information presented in this central figure in the next few slides. To begin with, we will again review the mechanism of energy storage in an electrochemical double layer. When I say planar, I'm not typically referring to a completely flat interface. All I'm saying is that it's a non-porous material. So when you have, let's say, such an electrode in a capacitor, an electrochemical double layer capacitor, there is charge that is stored at this interface, right? Because of this may have a positive charge, because of which the double layer formed has a positive charge in the metallic conductor and the negative charge in the electrolyte side. So this is the dominant mechanism. This can be quite fast, right? The adsorption onto the surface can be quite fast, and the desorption that may occur during the discharging of a capacitor can also be quite rapid. So adsorption, desorption is the main mechanism. And the species that are getting adsorbed and desorbed are charged species. This is the fundamental way electrochemical double layer capacitor stores energy. The extent of charge stored or charge adsorbed depends upon the surface area. So there are a variety of efforts to increase the surface area. All these strategies in some ways involve porous electrode, and even in a porous electrode, even though the ions are accessible into this material, in some ways still the storage, energy storage, charge storage mechanisms involves adsorption and desorption onto a surface. So there is a charged species getting adsorbed to a charged metallic conductor and so on. So this refers to planar, this refers to porous, as opposed to these two just simple adsorption without further electron transfer. There can be pseudocapacitors. This involves a Faradaic reaction on the surface alone. The most well explored system in this case are oxides of ruthenium and oxides of manganese. So what happens is that, let's say a proton may react with these particles. This is indicative of these particles, and a Faradaic reaction might occur. So this is complete electron transfer occurs, and there is a charge that is transferred from the electrolyte onto the material. Okay, so this is more or less like a reaction. This is a reaction, but the most important thing to notice is that this reaction occurs only on the surface. So this reaction doesn't percolate into the bulk of the material. So again, we want to have very high surface area, because this mechanism can occur on the surface. Consequently, we can increase the capacitance significantly. This mechanism is called pseudocapacitance, and the capacity of a pseudocapacitor is much more than a simple electrochemical double layer capacitor. So all these things the capacitors can be characterized by cyclic voltammetry. We have addressed this. So here, because Q is equal to CB and C is independent of V, we can say I is equal to capacitance times dV by dt. So in a cyclic voltammetry experiment, we change the voltage with respect to time. We typically have a particular scan rate. Let's say the scan rate is typically denoted by nu. If this is a constant, this is a constant, so I would be a constant. So this is what you would have, right? So at a particular scan rate, as the potential is getting changed, you would have a current corresponding to this quantity. So this is a signature of a capacitor. This rectangular schematic behavior is a signature of a capacitor. So there is another experiment you can try to do, which is the galvanostatic discharge. So that is, you discharge or charge the capacitor at a particular current rate. Okay, so you keep current the same, and then you discharge. So when the capacitor is completely charged, the potential is at the highest. As it is getting discharged, Q is getting changed. That is, the Q is getting decreased as Q scales linearly with the potential. When the charge stored in the capacitor gets decreased, the potential from the capacitor also decreases. Important thing to notice is that if you have a capacitor, let's say what we may refer to as an intrinsic capacitor, whether the material contains a nanomaterial or if it's a bulk material, that is, contains particles which are much larger, let's say micron-sized particles, the behavior is independent of the particle size. That is, as the charge gets decreased linearly, the potential also gets linearly changed. So this is independent of the particle size. We may refer to this as intrinsic capacitors. So the typical symbol that is used is nu is dV by dt. This refers to scan rate. If you increase the scan rate, the amount of current also increases. So this behavior is condensed into this formula. I is equal to A times nu to the power of B. B is approximately 1. So when you do an experiment and get this behavior and B happens to be 1, you can say that material is predominantly behaving like a capacitor. In contrast to capacitors, what happens in a battery is that, let's say the common lithium-ion battery, the lithium-ion intercalates into a 2D material. So what do we mean by that? When you, let's say, you discharge and charge a battery from one of the electrode, in a charged state, let's say in a typical lithium-ion battery, in a charged state, lithium-ion is in between the layers of graphite. As the battery gets discharged, this lithium from the graphite anode gets into the electrolyte, and then from the electrolyte, the lithium gets intercalated into the cathode material. Okay, so the cathode material again can be layered cobalt oxide, LCO, LMO, and so on, lithium manganese oxide, and so on. So these are the 2D. This is like a 2D material. This is like atomic layer thick, and lithium gets in between the 2D layers. Okay, so that is one way mechanism. Or even if you don't have a 2D material, there are always pathways for lithium to diffuse into the electrode. This diffusion phenomena can be slow. It might have activation barriers, and the lithium might also, in some cases, form a new compound with the already existing materials in the cathode. All these things, that is the diffusion phenomena with its own activation barriers, formation of a new compound, all these things are relatively slow processes compared to the processes that occur in a capacitor. So it's important to understand that the lithium gets into the bulk of the electrode material. Okay, it's not just a surface reaction. So the entire material has 2D planes, let's say 2-dimensional layers, and the lithium intercalates and gets into the bulk of the electrode. So if you again do a cyclic voltammetry, so there is a distinct feature of a battery. That is, as the scan rate changes, I mean, scan rate is the same. Let's say you operate the cyclic voltammetry at a particular scan rate. So the potential gradually changes. This reaction would occur only at a particular potential. Okay, so it will not occur in this region. So it would occur only at a particular potential, and there is an onset potential because of which the current increases. And even though you are scanning further in this direction, the thermodynamic driving force for lithium intercalation might be greater as you go further, but the number of sites available for intercalation would decrease. So because of decrease in that number of sites that are available, the current starts decreasing. And once all the possible sites wherein lithium can bind, if those sites are exhausted, there are no more sites that are available for further lithium uptake. In this case, the current gradually comes down and goes to zero. So when you reverse the potential, as you come in this direction, the lithium might intercalate, okay, de-intercalate. That is, again, as the potential goes this direction, the driving force for de-intercalation, that is the lithium which was bound, can come out. And as you go further in this direction, the driving force, that is the thermodynamic driving force for de-intercalation, might increase. Even though the thermodynamic driving force for de-intercalation increases, the number of lithium ion that are going to de-intercalate gradually decreases, because of which the current decreases. And if all the ions have been de-intercalated, the current gets back to zero. Notice that this can be fairly reversible. Okay, if the structure does not change dramatically, then you can do this multiple times, and you may have a reverse. That is, with each cycle, the cyclic voltammetry signature will predominantly be the same. That is, the magnitude of the current will not change if the structural changes are insignificant. Or if the structural changes are insignificant, the number of cycles that are possible is also large. So this signature has to be contrasted with this signature. Okay, this is a signature of a battery. We are plotting the y and x-axis are one and the same, and the nature of the experiment is also the same, cyclic voltammetry. But here you have a rectangular shaped cyclic voltammetry. But here you have a sudden peak on either side of the scan. So in this case, you have a behavior wherein the current is constant times scan rate to the power of 0.5. Okay, the square root dependent is typically dependent on diffusion in semi-infinite material. Okay, this is common in many transport processes occurring, heat transfer, let's say mass transfer. We have looked at how to quantitatively think through the transport phenomena mathematically in an earlier lecture. Please refer to this. But the important thing is that I goes as square root of scan rate. Okay, as opposed to that, here I goes as linearly with respect to scan rate. So as I mentioned that the lithium has to get into the bulk of the material, let's say during charging and discharging, to increase the rate of charging and discharging of a battery. It's good to have nanomaterials. Okay, then if the nanostructuring is undertaken in the battery electrodes, the extent to which the lithium ion has to percolate inside the particle, that distance is smaller. The nano materials have smaller size. Therefore, the lithium ion can easily get from the surface to the bulk of the material. Okay, so because of this reason, a lot of effort has been made towards using nano-structured electrode material in a lithium-ion battery. So when you do that, because the nano-structured materials, the amount of surface to bulk is more. That is, you may have large surface area as opposed to the material within the bulk. The behavior of bulk-like material is very different from nano-structured battery materials. So in a bulk material, that if the electrode material are, let's say, has large particle size, let's say micron size particle size, what you do observe in a galvanostatic discharge experiment is that when you discharge at a particular current, as the amount of charge that is stored as it decreases in a battery, the expected behavior is that the potential during, let's say, discharge, the potential is not going to change. Okay, so this is what we want in a battery. You want constant voltage as the battery is getting discharged at a particular discharge rate, at a particular current. Okay, so you want a flat potential change. But if the battery material is made up of nanostructured material, what you observe is that you see a linear decrease in potential as the charge gets decreased. So why is this important? This behavior is very different from this behavior, right? This behavior is typically goes in this form. That is, I is proportional to square root of scan rate. But this behavior, in this behavior, I would go as linearly with respect to scan rate. I is linearly proportional to the scan rate. Okay, so this behavior is more to do with a capacitor, right? So as we noticed in a capacitor, irrespective of whether the particle is a nanoparticle, nano-structured capacitor electrode, or a bulk material capacitor electrode, you always have this kind of linear material, linear change in potential as the charge gets decreased. These kind of materials, or this kind of behavior, this kind of capacitive behavior, may be referred to as intrinsic pseudocapacitance. Okay, so the pseudocapacitive behavior is innate. That's what we mean by intrinsic, in the sense that whether it is a nanoparticle or the bulk, the potential always decreases linearly with when the charge gets decreased. Okay, and the I is always proportional to scan rate. But in this case, you may refer to this kind of behavior as an extrinsic pseudocapacitance. That is, the same material, when made as a nanomaterial, would show this kind of a behavior, which is like a pseudocapacitive behavior. However, thus that material, when it is made bulk-like, behaves more like a battery. So when you have this kind of a mixture of material, part of the material might discharge in this manner, and part of the material, even though they are compositionally same, because the particle size might vary, some part of the material might get discharged in this manner. So the I versus scan rate is neither, in this case, it is neither B equal to 1, which is like completely, let's say, an ideal capacitor behavior, or B is equal to 0.5, which is an ideal battery-like behavior. It may fall somewhere in between. It may be 0.8, 0.7, and so on, which is indicative of the material having both bulk-like battery material and this kind of extrinsic pseudocapacitive material. So why is all these things important? Of late, there are some reports wherein one claims to have a capacitor with very high energy density when they're discharged at low discharge rates. Okay, so when you want to be thinking about a capacitor, you want to be discharging, doing the metrics of obtaining the metrics of a capacitor at high charging and high discharging rates. You cannot afford to discharge it at low discharge rates and claim to have a high energy capacity for your material. Okay, so this has to be really contrasted, and you have to quantify to what extent you have a capacitive behavior and a battery-like behavior in your own material. So please read this manuscript and the further references that is quoted in this material. Is this very important, especially if you're working on developing new materials for supercapacitors. Overall, we reviewed the underlying mechanism between electrochemical double layer capacitors and pseudocapacitors. Specifically, we looked at battery materials which are nanostructured. In this case, the behavior is more complex. Even though you are looking at a battery-like material, you may have a pseudocapacitive behavior. That pseudocapacitance is born out of nanostructuring. So you refer to that behavior as extrinsic pseudocapacitance. This has to be contrasted with intrinsic pseudocapacitance. So this is very important in quantifying the metrics of pseudocapacitor. So your increase in energy density can be artificial because you have sort of a battery-like behavior in your material. So please also go through this manuscript and the references quoted. Thank you.